golly. Oh, wait a minute, it's curving up away from the plane. Oh, my goodness. Wow, that's fascinating. What a fine video this is.
When we add another mirror, things get considerably more interesting.
Well, I do hope so.
Again, we can tilt the mirror backwards and forwards.
Oh, golly. Oh, golly. Now, you're not telling me I'm going to see an infinite expanse of me moving forwards. Why, there it is. Oh, wait, now it's curving down into the plane. Oh, wait, it's curving up away from the plane. Now, that's not an infinite expanse, is it? Does it loop back around? Oh, I don't know.
By lining up two mirrors edge to edge, we can see what is called dihedral symmetry.
Why, looky there. Why, I do believe I see 4 images of myself, and only 2 are mirror reflected. Why, look at that. I see 8 of me, and there's only 4 mirror reversed. Would that be 6? Why, looky there.
When we add a third mirror, we can see reflections extending across the entire plane.
Now, what would that look? Oh, God. Now, what kind of triangle's that? Do you mean to tell me that if I reflect across the sides of an equilateral triangle, I'll get an infinite expanse of images of me? Is that what you mean to tell me? Well, now here, I'm noting that all the lines of intersection are parallel to each other and perpendicular to the plane I'm on. Is that right?
That's right.
Wow.
And we can do it for different mirror arrangements, too.
Oh, no way. What other kinds of triangles can you reflect across their sides and see an infinite expanse of images of little old me? Why, that one ought to do it. Yep, sure enough, the 45-45 90-degree triangle can be reflected across its sides to produce an infinite expanse of images of little old Dexter triangle. Wow, looky there.
You've just seen how kaleidoscopes work.
Sure have.
They're made of mirrors that reflect the same image many times.
Sure are.
You've also seen that tilting a mirror causes the image in it to tilt as well.
That's right, we saw that.
Now, watch what happens when these two ideas get combined.
I'm watching. Now, what kind of configuration of mirrors is that?
The kaleidoscope's mirrors are arranged along the planes of symmetry of a cube.
No way.
The chamber itself is 1/48th of a cube.
1/48th of a cube. Wow, look at there. There's 48 images of me arranged artfully on the faces of a cube.
Can you see the figure reflected in the mirrors?
I do believe I can.
Same arrangement of mirrors can show many different shapes.
Why, look at that. The octahedron appears to have the same reflective symmetry as the cube. Now, what configuration of mirrors was this again?
1/48th of a cube.
Why. And what configuration of mirrors is this one?
1/24th of a cube.
Oh, my. Why, I see a rhombic dodecahedron. And looky there. That was a cube octahedron, and now it's a cube. Is that a tetrahedron with 24 images of me arranged artfully on its faces?
You can recreate the shapes you've seen here so far with a computer program such as Kaleidotile. However, you might have a little more trouble recreating this next sequence.
Oh, my. Now, why, looky there. Now, what is this? Is this a tetrahedron that's been reflected across its sides to fill all of space with images of little old Dexter triangle?
Yeah, all we did was add a fourth mirror.
What kind of tetrahedron was this, anyway?
It was a tetrahedron made of 1/24th of a cube.
Wow. Do you think all the little boys and girls out there can make their own kaleidoscopes?
I think they can, and the instructions are in the Kaleidotile teaching program.
Wow, that sounds quite interesting. You know, that sounds mighty nice. That sounds right fine. shell of 12. Here's the shell of 20. Here's another shell of 12. That's 45. Then a shell of 30, just totally flat on the outside. Yeah. What? Oh, I just mean a sort of a band of 30. Yeah. Right now. Like if you think of a latitude, if you think of a sphere, 30 dodecahedral. So if you think of the sphere as having latitude, the analogy is very similar to this. There's one at the top, a ring of 12. The tips are cut off. Okay. So this is actually the model.
Leave it next to it. Let it re-inflate it.
I need to send these back to him, actually. These models have really been useful today, though. This is the second time.
It's amazing that it fits together. I mean, given that.
The zone tools? Yeah. Well, the zone tools are right. That's the thing. The zone tools are right for all kinds of stuff. Like once I sat and I calculated the stellation pattern, or at least partially, of the tricontahedron, which is a very, it's a really nasty computation, but it is, I mean, you could do it on a computer, so it's pretty quickly, in some sense. But the zone tools are right, so that the calculation was easy. In some senses, you could in a day or two.
I love these kind of yellow. I love these kind of yellow circles.
Welcome to the Geometry Center's fascinating home page on the World Wide Web. Let's click a few random buttons. That one looks good. That one looks pretty good. Well, that one looks pretty good. Hey, that one looks great. So, this is my home page. I thought I'd archive it. There's a little picture of Eli. We've got a couple of snapshots off the back of that. It's strange watching it scroll. That's a photograph I like a lot. Now I just realized I don't have a way of going back.
Alt B.
Alt B.
No, actually Alt Alt
Okay. I should make this into a scratch tape too. So there's some feedback from my TV. Some more feedback from my TV. This looks a lot better on the screen. The computer screen. I don't think this is working out so well. There's something on my research. Let's take a closer look at that. There's some interesting examples of things I've been thinking about. Uh-oh. Good thing I checked that. So this is something that was a pretty productive use of soft image at the Geometry Center. That's a kaleidoscope with cylindrical mirrors that illustrates the 5-4 reflection group. And here's one with spherical mirrors. Oh, what? Don't want to do that. In a second we'll see this sort of in action, but here's some dodecafoam. I've been waiting a long time to see that. Here's something kind of cool. And let me just kind of close with something else. So there's a still picture of dodecafoam, and there's a great number of these on hand. That's sort of typical. So this is actually inside of the foam itself. This was a consequence of interacting with Bruce Shapiro, a local artist who's thinking about very interesting stuff. If you start with a 3 coloring of a hexagonal lattice, color one of the colors, say dark blue, call it null, and then repeatedly note that the null colors form a hexagonal lattice as well, and 3 color that. Then larger and larger structures will emerge, and eventually you'll have interlocking fractal trees. This generalizes. There's some tiles that reproduce it, and he made me some art. I guess one last thing, and then we'll stop doing this. So these are some materials made for the Math 5337 class this spring. There's a whole bunch of stuff. It turned out to be about 100 pages. And let's just go through one or two of these. So, began with symmetry and culture. What are congruences? One of the magical things about hypertext is that if you have the correct software and the correct computer, you could click here and an interactive version of this image would appear. And just kind of goes on and on. So I think that's it for my stuff. And in fact, I think that's it for Netscape. So what's this? Do you know, Lori?
Forgot.
Oh, well,
Projective plane.
yeah, that's right. It's a lattice of conics on the projective plane. So Matt Frank was here, and he's selling the world on projective geometry, and he certainly sold me. So this is, this started out as a lattice of disks on a plane tangent to the unit sphere in three-dimensional space. And then the plane has been sort of retracted onto the hemisphere simply by normalizing all the vectors pointing to the points. And then to make it sort of, so that would give it to put the thing on the projective plane, and to actually take the double cover and put it on a sphere is what will happen next. So let's just see what this looks like. So one thing about this is that it's certainly no accident that if you look around in any little region, it looks like all the circles are in perspective. That's because this is an expository on projective geometry. Another sort of thing is that any conic on a plane in space, when it is retracted onto the projective plane like this, will be one of these squashed ellipses. So this is sort of a generic picture of what conics are like. And beyond that, it's just kind of fun to watch. there's this artist who does 6-point perspective on the sphere. So this is a little different. This is infinite point perspective on the sphere, but the infinite points are around the boundary, around the equator in this case. This is the line at infinity. Okay. See it? Okay, well, what's this? This is a family of concentric circles that have been stereographically projected into the plane, tangent to the unit sphere, and then projected down onto the projective plane. So some of the circles went one way on the plane, and some of the circles went the other, and this was probably a circle that was projected to a line in the plane. So it's kind of neat to watch. That's another thing that can happen. Of course, these could have been projected to conics first and then projected to this projective plane, and it would have looked pretty much the same. So this, I can't quite remember what it started out being, but I believe it was a family of concentric circles in the plane. The center about which the things were concentric was quite far from the point of tangency with the projective sphere here, and this is kind of the result. Kind of fun to watch. So this, I believe, was two hyperbolas that were concentric. You know, they were sort of parallel to each other. They were just simply one was shifted along its axis to produce the other one. And then they were, of course, on a plane tangent to the projective sphere, and they were projected back down. However, of course, again, if they were projected to any other plane tangent to the projective sphere, they simply would have made two other conics in some other relationship. At any rate, I think this sort of shows a pretty generic situation. Point of reference is the dodecahedron. So I was wondering, can we fill up all of space with a fractal froth of dodecahedra? Of course we can. I wouldn't be bringing this up. So the point is that we use the stellations of the dodecahedron to create a substitution system. And in particular, what we want to do is if we can fill out a large dodecahedron with lots of little tiny dodecahedron, then we can either do one of two things. We can either then keep subdividing and get like an infinitesimal mash of dodecahedra, or we can repeatedly inflate and tile larger and larger chunks of space with dodecahedron that are all smaller than, say, 1.5 inches across. So let me show you a little bit about that. Okay. So anyway, here we are filling out the first stellation of the dodecahedra with little tiny sprinkles of dodecahedra. This is a pretty fast machine, so happened pretty quickly. I can't even tell if it's still going, but the point is that this is the first stellation of the dodecahedron, and that each one of these little hats, if I can find the arrow, each one of these little hats has been placed on the dodecahedron and is in turn made up of little tiny hats. It's hard to see how they exactly fit in here, and then also one other kind of piece, a little wedge. So we'll see in a second what happens when we move to the second stellation of the dodecahedron. Okay, well, this is the second stellation of the dodecahedron. We've added our little wedges. Notice the pentagons cutting through the faces, through the, this is the great dodecahedron. And this thing is just chock full of dodecahedra. It's kind of fun to watch it draw. There are the hats, there are the wedges. Now we go through and we sprinkle in all the delicious little tiny dodecahedra. It looks raggedy for a minute, and then as more and more detail is put in, it begins to smooth out. And there we are. Here we've added very long spikes into those sockets. This model is much larger than the last one. All that we saw before is just in a little tiny bit here. Now this is a kind of a hard image to read. Let me try rotating it a little bit, and in a minute I'll put up something a little different. But basically there are 20 spikes, 23-sided spikes coming out of the faces of an icosahedron, or the sockets of the great dodecahedron. One other thing is that the tips of these spikes, that's a nice one, the tips of those spikes lie on the vertices of a large dodecahedron. So we're almost done tiling out a large dodecahedron. But remember how small our original dodecahedron was. You see that pentagon there? That was the same size as the pentagonal faces of the original dodecahedron. Let me just try one thing and see if we work. So there it actually is drawing. Let me load in a larger image of the same thing. So this so I'm not really sure what's happening, but perhaps it's loading an even bigger image, if we're lucky. But it doesn't matter. Let's move on. So here we are actually drawing in the spikes with more detail, and I think the sort of more of the structure appears. So that's a little more what the final stellation of the dodecahedron looks like. But it takes it quite a long time to draw. And what on earth is this? Well, between the spikes we can fill in these really weird shaped pieces, and sort of once we've done that, we begin to really flesh out our very large dodecahedron. So this actually should be viewed as a dodecahedron with star-shaped notches cut out of its faces. It's kind of difficult to read this image, but if I can find the cursor, there we go. There's one of the pentagonal faces of our big dodecahedron. There's another one, there's another one, there's another one. And all these little tiny dodecahedra, well, the big dodecahedra on the edges here, are actually the same size as the original dodecahedron that we began with. It's the golden ratio cubed. So here we are filling in the final bits of our dodecahedron. And we really have done it. So look at all these little tiny dodecahedra. That's pretty amazing, isn't it? It's quite fun to watch. It just sprinkles them in. Let's see if we can get this to redraw it again. It actually is still drawing. This particular image has about 2.5 million polygons that make it up. And I guess it's also worth pointing out that the pattern that you see is not simply on the surface of this thing, but is really a three-dimensional analog to the pattern that you see on the surface. So what were the pieces that made this up, and how is dodecafoam really structured? I mean, this is in a way the most interesting question of all. So again, it's based on the stellations of the dodecahedron, and a stellation is made by taking the facial planes of an object and extending them forever, and it chops space up into a few fundamental kinds of pieces, one of which is a five-sided cone. Now, these dodecahedra all lie inside of one of these five-sided cones, which I call a hat. And in particular, though, notice that, see, a hat can be broken up into smaller hats. One there, 5 around the base, and a single dodecahedron. So that's 6 hats, 1 dodecahedron, and then there's some other piece that fits in here, which I call a wedge, which is the cell that you get from the second stellation. Let me just translate this over and maybe make it a little smaller. And load it. So here we have the second piece as well as the first. So here's the hat, and here's the wedge. So the wedge is a particularly nice and interesting shape. I have it here fleshed out with more dodecahedra, so it's a little easier to see what's going on. One thing that's extremely interesting to point out is that there's certain rules for how the dodecahedra can possibly fit together. I call them the 1, 2, 3 rules, and they're really quite simple, and they guarantee aperiodicity, but although a slightly more general structure might emerge. So the first rule is can only be seen in the wedge piece. In the wedge, you can see that if dodecahedra meet vertex to vertex, they must differ by exactly 1 power of the golden ratio. This is difficult to see, perhaps, but it is there. See, this one actually meets this one on their vertex, which is hidden inside of the wedge, and they differ by 1 power of the golden ratio. These two meet at a vertex hidden in there somewhere, and they differ, and so forth. And we have a tower of these things. Along the side, you see them quite a bit. The 2 rule is sort of similar. If 2 dodecahedra meet face to face, and the center of, and the centers meet, then they differ by 2 powers of the golden ratio. And then the final rule is the 3 rule, which is that if 2 dodecahedra meet vertex to vertex, edge to edge, they indeed meet, they differ by 3 powers of the golden ratio, or in fact, they actually are the same size. The 4 rule is kind of technical. It just is that there are no chains of 4 dodecahedra that are actually at the same scale. This is actually enough to guarantee aperiodic and very strange structures in the space. I guess I won't put up the wedge or the spike or any of those blah blah blah. Really, I just kind of want to have these pictures somewhere where I can show them. So this is the view inside of the orbifold taken by a reflecting S2 cross S1 across its meridional sphere and its meridional torus. So basically we're inside of a silver tin can. The whole thing has a piecewise flat geometry. All the curvature is concentrated along this torus and this sphere. Basically, this was made in soft image. It was rendered, ray traced, and it's simply a camera with some lights and an icosahedron with my face texture mapped on it, and some salmon tetrahedra. And the whole thing's in motion. One thing that's particularly interesting is notice how the geometry of the space seems to actually depend on the position of the viewer.
Let's try another one. So here we have a similar kind of situation. This time it's a little less cluttered. Kind of reminds me of heaven. That's an interesting spot right there. The actual orbifold is pretty small. It's only about twice as tall as the icosahedron. Unfortunately, these images are too big to fit on a TV screen the way they're set up right now. But these are the trilobite tiles. You can see how they fit together, I think, a little bit. This. Oh my goodness, oh my goodness, oh my goodness, oh my goodness, oh my goodness. There aren't too many frames here, but I think you can get a feeling. Let's slow it down a bit. This is a camera moving around inside of a special kind of kaleidoscope. It's a little overly foreshortened, and obviously I didn't render enough of these, but each one of these took like 20 or 30 minutes or something to render. It's actually an octahedron with 90-degree dihedral angles, so they fit 4 around an edge and 8 to a vertex. It's the idea is that the sort of developing space, the space which you should be able to see, is actually sort of a tiling of hyperbolic space, but where the chambers are flat and all the curvature is concentrated along these mirror planes. Hi, Anna. Do you recognize this one?
Is that the icososcope?
No, indeed, it is not.
Then I have no clue.
This is the icososcope with a spherical mirror tacked onto the end, so that the idea is that this would make the, I guess, the 120 cell. It's supposed to have the symmetry of the 120 cell. I think the viewer can judge the success or lack thereof for oneself. I wasn't really very happy with it. Want to venture what this one is?
Well, I see some 5-fold centers, but I really wouldn't want to venture a guess.
It's the icososcope. So here's a little bit more of the icososcope. So this is one of the few kaleidoscopes that I rendered that can actually be physically made without too much difficulty.
Do you have the mirrors completely reflective?
No, not, well, yes, in this case they are completely reflective, so they're totally transparent, but most of the time I have them shaded to about 97%. So, This is the ideal triangle in the hyperbolic plane. That's something kind of similar. This is in the dodecaplex. Oh no, the Seifert-Weber dodecahedral space. There it is with the reflectivity turned off on the mirror, turned on, turned off. There's in the sort of the Seifert-Weber octahedral space, so to speak. And here's the same thing with the mirrors turned on a little bit better. So it's the octahedron with dihedral angles of 90 degrees. This is the ideal triangle in the hyperbolic tetrahedron with mirrors on the top and bottom. Here they are without the mirrors on the top and bottom. I'm going to slow this down a bit. There's the ideal triangle in hyperbolic space. There's the dodecaplex again. So this is a dodecahedron with, oh yes, with 90-degree dihedral angles. So it's not quite the Seifert-Weber dodecahedral space. And there it is again. So this is sort of the same space that you see in Not quite a bit. There it is again. We just watch these all day. I put in a little jelly cone in there so that sort of leaven the texture of the whole thing. So this is a particularly amusing arrangement of mirrors. This is a single kind of blobby object. It has been reflected in an ordinary kind of a mirror, and then the whole thing has been placed in a spherical kind of mirror. So this is actually the image in this flat mirror of the curved reflection in the back behind the viewer, behind the camera. So the question here was, could you make a kaleidoscope that accurately portrays the geometry of S3? And I think the answer is a resounding yes and no. The sort of the resulting space isn't homogeneous in the sense that or maybe it is. I don't know. I have to go. So this is a particularly interesting structure. It's inflations of this kind of cubic lattice. Each of these surfaces is kind of isotopic to the Schwartz surface. It is each one of them has the same sort of reflective similarities as the cubic lattice, and each of them divides space into two congruent parts. Similarity is acting on the cubic lattice that takes the green to the blue to the orange and so forth. And this similarity is what drives the aperiodicity in the trilobite tiles. I'll tell you in a minute. So this is the sort of the inner structure of my three bolite tiles. It's basically taking the previous images and chopping them up and giving them sidedness and making them look pretty. So this is pretty much what it is. Unfortunately, the images don't quite fit on the TV screen. So this is Ava Molnar and David Molnar's wife, Rose, on a Taurus. And I guess there's a lot more to this image, but it doesn't all fit on the screen. And there you are. That photograph of Ava's really cute with her hands out like that. Let's see about getting another one up. So this here is a kaleidoscope showing the tiling of hyperbolic space by pentagons with 90-degree angles where you reflect across the sides of the pentagons to fill out the whole plane. The icosahedron here is really foreshortened. It's actually just a perfectly ordinary icosahedron. It's just the camera is really close to it. So to really see this properly, you have to stand about 4 inches from your TV set. The red thing is just a blob. The green thing is a dodecahedron. The chamber is simply made with cylinders that are perpendicular to the floor. So this is the tiling of hyperbolic space with 90-degree hexagons where you reflect across their sides. It's got the same icosa, the same red blob, the dodecahedron. We've also added tubes at the corners of the hexagons to maybe get a little better sense of the way the tiling works. It's not entirely clear that every part of every chamber is visible, that this developing space is the same as the visual space. But I'm pretty sure it's the case in this example. So this is a little bit of soft image, just to sort of illustrate what's going on. So we actually here have the sort of a little bit of a scheme. These are actually the spheres that it took to make the dodecahedral kaleidoscope. They meet at 90-degree angles along the, their intersections. And anyway, it's a neat program. It's a lot of fun. So, also for example, this is how the 3-bolite tiles were made. And let's see if it'll let me drag it around a little bit. So as you can see, it's quite fun to use. These pieces can be assembled and played around with, and then finally the last step is to render them nicely. It gives a better sense, I think, of the three-dimensional structure, doesn't it, to be able to fiddle with them. It's a nice optical illusion. Well, my, look at the time. Guess it's time to go, but I'll have to put some more stuff on a little later today. Perhaps some geomview stuff. So that was the...
Right now. Yes, you're recording right
Okay, well, we got it now?
now. Yep.
Okay. Well, we switched computers. Am I not talking loud enough? This is my favorite computer, the Next. There's my browser. One of the wonderful things about the Next is that you can have your own little icons, and icons I have. Okay. So this is a tiling that was sort of discovered in the same instant by Joshua Sokolar and myself, thousands of miles apart before we had even met. And here it is, his version of this tiling. And he's found matching rules that seem to enforce it. In a little while I'll put up my version of the same thing, but we both thought for a little while that we had
discovered a single tile that would tile the plane aperiodically, and we were both wrong. Okay. Next up is another one of Josh Sokolar's pictures. This is a quasi-periodic thing in the sense that it's from the slice and project method, from a 12-dimensional lattice to the plane, and I think it's quite pretty. What? Colors are good? Yeah, colors are pretty good. So it reminds me of lily pads. Close that up. And it would be good to go ahead and close this up, quit that program for a little while, hide this, hide this. Okay, next up is a similarity tiling of the plane. This might be fun to watch draw. So let's see what happens. Oops. I'm not sure how that happened. I see. Well, I'm too lazy to restart the tape, so this is a similarity tiling of the plane. All these objects are similar, and they have quite a fascinating structure. And it's fun watching them draw. This was made in Adobe Illustrator. See that little wheel spinning? Okay, that was quite the showpiece, isn't it? Oh, it's still drawing. Okay, I guess we'll go ahead and close that one. And we'll look for... So here's another one on the same, along the same lines. It won't take nearly as long to draw. This is sort of a typical structure. You can't see it in this particular image, but in the PostScript output to the printer, you can tell that there's a variety of kinds of interesting singularities. And there's some interesting identities that one can derive. But the structures are really too small to be seen here, so I won't describe them here. Along these lines, one sort of special kind of singularity that emerges could be thought of as a Euclidean singularity. So, topologically speaking, this is an annulus, with one end in the center of the image and the other end at infinity. And it seems quite reasonable to view this as a sort of Euclidean structure, where Euclidean motions take these objects to each other. Actually, here's another kind of structure that's pretty similarly, very closely related, but the difference here is that if you repeatedly replace these hexagons with 7 small ones, or rather with 6 small ones, with rings of them, like here, you'll eventually get a completely periodic structure in the plane, unlike the other ones. So it's really very different in the limit, even though it seems to have the same kind of strange, bizarre structure before that. Oops. So here's another thing along those lines. This is a tiling of the plane with octagons. Notice that it actually is periodic in this picture, and I used to have something interesting to say about that, but I don't remember what it was. Here you can see how the image was actually made. So another structure that I was thinking a lot about are the black, white, and gray substitution system on the L tiles. And in fact, classical notions such as color symmetries can be extended to non-classical situations such as these substitution tilings. And this has a lot of really interesting properties. In a limit, if you keep these replacements up, the black regions in the limit are totally congruent. I mean, they're similar to the yellow, the white and gray. They make these interpenetrating tree-like things. Here are the actual rules. Down here, black goes to 3 blacks and a gray, and the second step after that looks like this. White goes to, gray, you can't tell, but that's gray. Oh no, it is white. Here, white goes to 2 blacks and a white, and gray goes to gray and 3 whites. I think actually I changed the coloring, since I think it's now drawn a slightly different way. But that structure leads to this aperiodic tiling of the plane. There's 2 shapes of tile here, a trilobite and a cross, and they must tile the plane aperiodically. Anyway, it's quite an interesting structure, I think. And set it for that. So I guess we will pause for a minute and get some more stuff up. Okay, next up it's stereographic projection from the sphere to the plane. So let's just see what we're doing here. So the goal here is to understand a way of projecting the sphere to the plane. And up here we see a sphere sitting on a plane. And in particular, the north pole of the sphere has been sent to some sort of really far away place. There's a flashlight sitting at the North Pole and projects straight down to the plane. So this point gets sent to here. The south pole, or this pole of the sphere gets sent to here. This little ring gets sent to this little ring. This little ring gets sent to this little ring, and so forth. The equator of the sphere gets sent to this line. Now let's watch what happens when the sphere moves. So as the sphere turns, notice in particular that, see, watch what happens to the image of one of these poles. See, there it goes. They go on, come off one side and come back on the other. Notice what happens to each of these circles. They grow smaller and smaller, then flip out the other side. Let's slow this down a little bit. Whoops. See these circles grow, grow, grow. Eventually a circle splits into a line and wraps back around the other side. More generally, a Mobius transformation is simply this kind of a motion with the addition of a translation and a dilation and a rotation. So Mobius transformations are really easy to understand once you understand this picture. Well, this is a picture of just the image in the plane. Let's slow it down a little bit. Maybe this is easier to understand, maybe not. Let's see the same thing with the longitudes of the sphere. So here is, just for fun, here's the longitudes of a rotating sphere. Let's see the same thing with the sphere set into the plane. I'm using Mathematica. So these were made in Mathematica. And then here's the same thing with just the longitudes projected into the plane. So actually this image might seem familiar to many people. One thing that's amusing is notice that the angles around these points are staying constant. The map is conformal. Here you can definitely see how circles shrink on one side, grow on the other, split into lines, and come back around. Looks kind of like a spider crawling. Now finally, maybe the most amusing thing is here's a spherical dodecahedron that's being rotated and projected into the plane. Notice that around these vertices the angles stay 120 degrees even as they move around. Occasionally a line shoots through the image, and that's just because of some problems with infinity. The way these curves are drawn is as little tiny line segments, and if the ends of the line segments, if the line segment was supposed to wrap around infinity, well, of course it wraps around the short way, I suppose, and causes this. I never did bother to finesse that. Here's the icosahedron. Another amusing thing about this particular little animation is that you can see at many different points, you can see the 5-fold symmetry, the 3-fold symmetry, and the 2-fold symmetry all in the same movie, just at different moments. Apparently this tape is going to be over in a minute or two, so I guess we'll have to get out another one. Let me go ahead and very quickly load up another movie. So So here's an old movie that some kind of superseded by some software that I have access to now, but well, this, I'm gonna have to pause it. Oh wait, here we go. Okay, so here we go. Here's the rotating stellated dodecahedron. Let's just skip that one. The computer's suffering memory problems. Maybe so. Anyway, here's another rotating dodecahedron. I think this is very attractive, this particular image. I think it's time to go get another tape. Now, who doesn't like Spirograph sets? So this is me, I guess. So this is a this is another old Mathematica movie. This tape is a continuation of the last tape, so it may just seem like an abrupt transition. But I'm just sort of trying to archive all my materials on the computer, or a bunch of them. So here's the original code. It's quite simple. It's impossible to read it on the TV screen, but it's just a couple of little parametric equations, and it makes beautiful pictures like that. And here's, oh, that's not the one I wanted to show you. First, this is what happens when we change one of the parameters. Oops, where'd it go? So the number of nodes depends on the greatest common divisor between the two. There's two parameters. Okay, now that was two wheels. If we have a third wheel, we have an outer ring and then a wheel moving within that, and then a wheel moving within that. This is the kind of spirograph stuff that starts to happen. Here, this is parameterized by the size of the third wheel, I believe. And it only went so far, but you can kind of imagine what might happen if the size of the third wheel were to grow. Pretty amusing. And I think we'll pause the tape. So a very nice thing has been to be able to render nice images of the dodecafoam stuff. So this is not a surface pattern. Again, this is a structure that is internal. It's made up of zillions of little tiny dodecahedra. And in particular, this image had, the object had about 2.5 million polygons. Of course, only a tiny fraction of those were necessary. This was made in Mathematica output to sort of write the transforms necessary for the substitution system. It made the thing. Then the system was iterated in a program used by Dan Kresh, which sent output to GeomView, which then sent output to RenderMan and made the image. So you can't see the whole thing at once here.
How many levels did you go to?
I don't know. Okay, let me get another thing up. To see this properly, you have to stand approximately 4 inches from your TV set. So, this is for you, Lee. Apparently a student here 2 or 3 years ago made all the 59 stellated icosahedra. So we can just kind of grab one and click. Is there a particular one you'd like to see? I can't see the buttons to load them in, so I have to kind of stab around until looks like there's 2 of them. Hang on. Okay, here's another one. Okay. Have you built this one yet? So there's another one. Magnus Winiger was here on July 31st and is apparently working his way through many of the stellations of the tricontahedron. They make the stellations of the icosahedron look pretty mild. But this one has some pretty neat symmetries. I don't know what this is. I have no idea. But this seems like a good place to stop.
That looks like a part of the sandwich of our omelets.
Yeah? Look at that. You would?
What if you draw a picture?
Oh, that's cool.
It will be another spiral.
What's that?
It looks like a spiral.
Yeah. A spiral.
A hat.
You know? Oh, that is cool. You know why it's making a spiral? It's because it's taking pictures of itself. That is really neat. Isn't that cool, Zoe? You making background music for this?
No, just television. Not on the nice tuny plate. I got the telescope. Roasty sound. Stop! Stop it! Stop! 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 Stop it! Stop it! Stop it! Stop it! Stop!
That's pretty cool, isn't it, Zoe?
No.
What is going on?
What is going on with this? That's
Is the TV freaking out?
No.
Do you think the TV's ever had anything like that on it before?
No. It scared me.
Well, it's pretty neat.
Bad country. April Fools.
Today is April Fool's.
No, it's daytime, it's nighttime.
So it seems like most of these effects come about from the boundary of the
Most of these effects come
screen.
Could you shadow the light, please?
Oh man. Golly, I haven't tripped in a long time.
To watch Robin Hood.
Well, Zoe, you're not going to be watching Robin Hood for a little while.
But I want to turn it on to Robin Hood.
Well, this is so cool. Look at this.
This is not cool. This is not really cool. This makes me sad. This makes me sad. Please, I don't want this whole TV on this.
Okay, we'll stop.
Please. That's what Washa does. What are you doing? Just waving your hand?
Yeah, look what happened when I waved my hand in front of it. It changed.
No. No.
Well, aren't you tired of clockwise? Let's try counterclockwise. Bread?
Yeah. My stomach wants some bread.
What's this look like?
A highway.
A highway, yeah. Looks like to me as well. Let's try it without this light. Yeah, this light really helps, doesn't it? It pumps something in there. Shot, and then we'll stop.
Oh, Dad, like King Triton's brown.
Oh yeah?
Oh, did you remember that spiral that I drew?
Yes, I do remember that spiral that you drew.
It was